So, today I shall speak about a very esoteric topic in signal processing. It is called quantum neural networks. So, what exactly is a quantum neural network? What is an ordinary neural network? An ordinary neural network consists of, say, an input layer in which you give an input signal ut and you get an output signal yt, and the mechanism which governs the relationship between yt and ut is defined by a set of weights and sigmoidal functions. Okay. And the aim is to identify a system. You have a nonlinear system with the same input coming to this, which produces a desired output dt. Okay, this is a nonlinear system, and you tune the weights in such a way so that if you take the error between these two, if you take the error between the desired output and the actual output of the neural network, that error process is a minimum in some sense. So, let us say you square it and you integrate it and minimize it. You minimize it by changing the weights, by tuning the weights of the neural network, right. That is how you design a neural network to identify a system. Now, you can do it in various ways. You can have if the system, nonlinear system does not have any memory, then you can use a feed forward neural network, which is gives you a direct relation between the output layer of the neural network and the weights and the input process u2. It is a direct relationship. So, you choose the weights in such a way such that the output of the neural network differs from the desired output, that is actual system output, by the distance between the actual output of the neural network and the desired output is as small as possible. You choose the weights in such a way by minimizing this error using the gradient search algorithm. So, you have some sort of an error between the two, f of w u norm, and then you minimize this with respect to w. Now, you can have a system having memory. If it has memory, then it is described by a stochastic differential equation, and you want to model that using a neural network. So, what you will do is you will use this is called a RNN, a recurrent neural network, which takes as input a ut process and it outputs a yt process, and the input states of the neural network are xt, that is the states at the nodes, and these nodes are governed by a differential equation or a difference equation. dxt by dt equals, say, some function of xt and the weights, and that is all, and the input, or if it is in discrete time, it is xt plus 1 is equal to f of xt, wt and ut, and the weights are to remain constant. So, you have you postulate a difference equation for the weights also. Wt plus 1 is wt plus some epsilon w noise. So, there is also some noise in this system in the neural network. So, you call it as wt plus 1, or let us call it some other name, let us call it as epsilon x t plus 1. So, in a recurrent, so this is a network, a neural network having memory, it is a recurrent neural network. That means the state at time t plus 1 depends on the state at time t and the weights at time t. So, if you want to estimate the weights and the state in such a way that the output of the neural network matches that of the given system, then you assume that you are taking measurements. So, you are taking noisy measurements of the system. This is nothing but the output layer. The output layer can be written, the output layer node can be written as a function of all the input layer nodes at time t. So, you put an h of xt or z at t is equal to of xt plus you can say some noise, measurement noise. So, when you measure the output is, you are taking noisy measurements of the output. This is actually the output of the neural network, and then you estimate your xt and wt using the extended Kalman filter applied to this measurement process. So, it is a simple difference equation based on well known extended Kalman filter theory. So, this is how you estimate the weights of a recurrent neural network. Now, why this fails in many cases? This fails to work well in many cases, because in many cases what happens is you want to estimate a continuously evolving family of probability density functions, and the output of an ordinary neural network will not give you an output which satisfies all properties of a probability density function. Namely, it should be integrable, it should integrate to 1 over all the spatial variables at each time t, and it should be positive definite. An ordinary neural network is just a functional relationship between the output y between the input u and the output and the weights, it is a function of the input and the weights and gives you an output y, and this y may not have properties of a probability density function. So, with that aim in mind, quantum neural networks came into being, and it is based on the Schrodinger equation. Schrodinger equation. So, what is the Schrodinger equation? Schrodinger equation is an equation of the form d psi t by dt, I d psi by dt is equal to a Hamiltonian, which is a function of certain parameters theta and psi t. So, this Hamiltonian is a self-adjoint operator in a Hilbert space, and because of this being a self-adjoint operator, if you solve this equation for the Schrodinger equation, this is a psi t takes values in a Hilbert space, and H is a Hermitian or self-adjoint operator on the Hilbert space. So, it naturally generates a wave function if at time 0 it was normalized to 1, but normalized to 1, then psi at all times t will be normalized to 1 for every t greater than or equal to 0. That is because of the nature of the evolution, which is governed by a self-adjoint operator. In fact, if H is not dependent on time, say H is a function of just theta, then you can write the unitary evolution operator as e to the power minus I t h theta, which is obviously a unitary operator. But if it depends on time, then you have to use a Dyson series like expansion and prove that it is unitary. To prove that it is unitary is not very difficult. You have to just compute any, you take any state vector u0 psi 0 and take ut, and you compute the norm of this square. So, the norm of this square will be nothing but ut psi 0 comma ut psi 0, and if you take the time derivative of this quantity d by dt of ut psi 0 with ut psi 0, what will you get? First you differentiate this ut, that will give you a minus I h of theta t or h of t into ut psi 0, psi 0, and then you differentiate this plus ut psi 0 comma d by dt of this is minus I h t ut psi 0, and since h is Hermitian, you can bring this to this side and cancel it, and this will give you 0. So, the rate of change of this quantity is 0. So, which means that if at time 0 it was normalized, that means at time 0 psi 0 comma psi 0 was 1, then at all times t ut psi 0 comma ut psi 0 will be 1, and ut psi 0 is the wave function at time t. So, if you want to design it practically, what you will do is you will use, let us say, a Schrodinger equation for one particle with Planck's constant as 1, that gives you dou by dou t of psi t x equals minus 1 by 2m dou square psi t x by dou x square plus you have something like v depending on theta t, v depending on theta t and x into psi t x. This is a potential, and you can control the parameters of theta t so that mod psi t x square, the density, probability density at time t of the position variable that tracks a given wave function ptx, that tracks a given probability density function ptx. You should track it as close as possible. So, this Schrodinger equation naturally generates a family at time t is equal to 0. If you assume that it was, this density was a probability density, the square of the wave function, magnitude square of the wave function was 1 integrated to 1, then at all times t it will be true, because this is a Hermitian operator. If you look at it as here h theta t equals minus 1 by 2m dou square by dou x square plus v of theta t x. This is a multiplication operator, this is a differential operator, this is a self-adjoint operator in the Hilbert space. So, at all time t psi t x square dx, this will be 1 for all t, right, it will be 0, it will be 1 at all times t. So, it naturally generates a one parameter family of probability density functions. And how do you update the parameters? There are various methods. First you discretize the equation. So, you write this equation as psi t x is equal to so you discretize the Schrodinger's equation. So, you write psi of t plus delta t x is equal to psi of t comma x minus I h of theta t. So, it is an operator acting on x, on psi t, it is a differential operator acting on psi t. So, you write it in this form, okay, and then you consider the given family of density functions which you want to approximate. Ptx, Pt plus delta Tx is the density at time t plus dt minus mod psi t plus delta t comma x square. This is a desired probability, this is the actual probability density of the neural network at type t, and you square it. Let us say you square it and integrate over all positions. So this gives you a sense, in some sense, the mean square error between the desired density function and the actual density function generated by the Schrodinger's equation, and you use the adaptation rule theta t plus 1 or theta t plus delta t equals theta t minus mu times dou by dou theta t, right. This gives you the recursive equation. That means that if the cost energy function increases with increase in theta t, then this will be positive. So at the next stage you will reduce it and so on. So this is a gradient algorithm applied to this. If you want to implement it, you have to substitute for psi t plus delta t x into this equation. So what you will get is that theta t plus delta t equals theta t minus mu times delta by delta theta t of integral Pt plus delta Tx minus, now psi t plus delta Tx is mod of psi Tx minus I h of theta t x acting on psi Tx, it is an operator. So you cut into delta t and then take modulus square and take whole square and take dx and differentiate this with respect to theta t. It is a fairly straightforward procedure, but there are other simpler methods to do this. Of course, you can ask one more question, that suppose you want the density which is being tracked, then Ptx is a family of densities which is being tracked by the magnitude square of the wave function. Now you want this tracking to be in such a way that the mean value of the signal corresponding to the wave function square, the mean value of the signal corresponding to this probability density function is highly correlated with a given signal. This happens, for example, in EEG data analysis, when you want to estimate the probability density function, joint probability density function of the EEG signals at different sensors located on the brain from the speech signal alone. You know the EEG signal is highly correlated with the speech signal, because if there is some small deformity in the brain, it will affect both the EEG signal as well as it will produce slurring in the speech. So you can say that your wave function square, if you look at psi tx square, this models the probability density function of the EEG signal and its average value into x dx. This gives you the average EEG signal at the output, and this should be highly correlated with the speech signal. So if I call this, if I call this quantity as m psi t, then you want m psi t to be highly correlated with, the speech signal. So what I do is I predict m psi t based on st and its past. Let us say I make a prediction of the form m psi t hat, I make a prediction of this as a1 or a0 st plus a1 st minus 1 plus so on, plus ap st minus p, finite memory st minus p. I make a prediction of this and I choose for a0 a1 ap, so that m psi t minus m psi t hat square, and you sum this, t equals, say let us call this as a t dash equals t minus d up to t. You make this is the prediction error energy, and you minimize this prediction error energy with respect to a0 a1 to ap by differentiating and using the standard methods in signal processing of constructing a linear predictor. So you minimize this with respect to a0 to ap, and suppose this gives you, if you minimize this function will be a function of the wave function, and it will also be a function of the speech samples up to time at times t minus 1 t minus p, then you go further up to t minus d, it will be a function. So this energy function will be a function of the wave functions, or you can say it will be a function of the m psi t dash and also of st dash, for t dash lying between let us say t dash lying between t dash greater than t minus d less than or equal to t. So you use this energy function. Now if this energy function is large, if this energy this is prediction energy is large, it means that the quantum neural network is producing a wave function with whose average value of the position is not highly correlated with ST, which means that you must adapt at a faster rate. That means you must increase the adaptation constant appropriately. So you can make mu as a function, you can make the adaptation constant as a function of let us say some increasing function of this error. So you can call this as, let us say, error energy, for example, you can call it as 1 plus alpha times this error of these two, m psi of t dash, m psi of t dash, st dash, t dash less than or equal to t greater than or equal to t minus d. So you make this adaptation constant increase, so that when the error is large, prediction error is large, then it increases, the algorithm adapts at a faster rate. So in that case you get an adaptive algorithm, namely you get theta t plus 1 is equal to theta t minus mu delta by delta theta t. Mu is a function of t, of integral of p t plus delta t x minus psi t x magnitude minus I delta t h at theta t x psi t x square dx, right. If you differentiate this and you make the adaptation constant increase, so that if the prediction error energy with respect to, if your mean value of psi t at time t, mean value of the wave function at time t is not correlated, highly correlated with ST over the past d samples, where S is the desired signal, then you make your adaptation constant larger, and if it is highly correlated, then the prediction error energy becomes smaller and you decrease the value of the step size mu t. That in summary is what a quantum neural network does. But there are other approaches to the quantum neural network, namely based on the Feynman path integral. Feynman path integral. So there is another method to get the solution to Schrodinger's equation, which is through the Feynman path integral. It is based on the fact that if L is the Lagrangian of the particle, in this case you call it, you say it is a function of xt and x dot t, okay. If you take a Lagrangian function, and you can also make it dependent on theta t, some parameters. So you can write it as, so if it is the case of a, say, a classical particle, then you can write the Lagrangian as the kinetic energy square minus the potential energy square given theta t, where you make the potential dependent on theta t. Then it is known approach to quantum mechanics. So it is known that if you compute exponential integral from 0 to t I times this, and the action function, namely Lxt x dot t given theta t, say t dash t dash t dash dt dash. If you compute this action functional corresponding to this Lagrangian over 0 to t, and you take the path integral of this, that is, you sum this over all possible paths. By dx I mean, when I say dx, it means that the product of dx t dash less than or equal to t, you are summing over all the paths between 0 and t, and you sum it up in such a way that x0 is equal to some a, okay, x0 is equal to a, and x at time t equal to b, and you put a normalization constant c, then it is known that this, if you call this kernel as kba, then kba provides the unitary evolution kernel for the Schrodinger equation. That means that what happens is that if you look at ktba, this quantity, it will also depend on the history of theta up to time t. So you can write it as theta s as less than or equal to t, because the potential dependent upon all that, and if you multiply it by the wave function at time 0, namely psi 0 a dA, if you multiply this by this and integrate, then it will give you psi t at time, the wave function at time t, and evaluated at the point b. This satisfies the Schrodinger equation. So you can use this formalism also to design a quantum neural network. So what you do is very simple, it's very simple. You simply take psi t at b, you look at psi t plus delta t at the point, let us say x, at the point x you find this out. So, you can write this as psi tx. Now, let us do it this way. You write this as right, this is nothing but integral of the path, you take the path integral. So, it is exponential I x, then the action function, the integral of the Lagrangian is called the action functional. So, it can be written as s of x s given theta. Okay, it depends on the entire path up to time t. So, you call it as st, path up to time t, say you call this as psi t at x, okay. And then you put dx, so this gives you the transition probability, or if you multiply, you take over all the paths. Okay, let us do it this way. You take on you multiply it by the wave function at time 0. So, let us call it as x 0, dx 0, and then d of all the path, d over the whole path up to time t. That means dx tau you take for 0 less than tau less than or equal to t. So, this will give you the wave function at the point x t at time t. And then I want to differentiate this quantity with respect to the parameter theta t. How will I differentiate it? In order to apply, in order to minimize the distance between, let us say I want to minimize the distance between the given probability density function and mod psi t of x square. I want to minimize this distance dx, I want to minimize. So, of course, you are doing it at time t. This x is, when I say x, it means it is at one point x at time t, evaluated at time t. So, you have, for that you have to be able to differentiate psi t x with respect to the parameters, but you can do that very simply. You see, if you take psi t of x and suppose you take dou by dou theta t, you are differentiating it only with respect to the last variable. So, that will be equal to simply s x theta is the integral of the Lagrangian up to time t. So, it will be simply dou L, it will contain only the last term. So, it will be L of x t x dot t given theta t by dou theta t multiplied by exponential I s t x given theta, and then you put a psi 0 x 0, put up psi 0 x 0 and you put d x 0 and d of all the path up to time t. So, you can directly differentiate this and apply this to the gradient algorithm to this. Now, you can ask more difficult questions in the design of a quantum neural network. Like, of course, you can ask what is the convergence rate. When you measure the probability density, you may make errors in the measurement of the density, you may make measures in the measurement of the reference process to which the output of the quantum neural network is, the mean value is supposed to be highly correlated. So, such measurement errors will cause the parameter trajectory to fluctuate slightly. So, you will get equations. If you linearize these parameter fluctuation equations of delta t around the nominal value, you will get delta t plus 1 equals delta theta t, plus you will take the variational derivatives of all those cost terms with respect to theta t. So, you will get something like f1 of it will be a function of time t multiplied by okay, it will be of this form, it will be nothing but f1 of t multiplied by delta theta t plus f2 of t multiplied by delta pt, where delta pt is the reference probability density function arranged in the form of a vector whose spatial samples have been arranged in the form of vector, and this delta pt denotes the measurement error in measuring delta pt. Then you could have a measurement error in measuring the signal to which it is correlated. Of course, you are using all the signals of the past. So, if I call say st, if I denote that vector by st, that means this is st minus 1 etc. st minus d. If I call this as this whole vector as vector t, then it will involve something like delta st. Okay. So, if you know the statistics of these fluctuations delta pt, delta st and so on, then you can calculate the statistics of delta theta t plus 1. You can use large deviation theory to control the parameters in f1, f2, f3, so that delta theta t does not deviate from 0 by too large a value with a large probability. That means you consider the probability that delta theta over the whole path norm is greater than epsilon. You want this to be as small as possible. So you compute this probability using large deviation principle by using the formula for this deviation probability in terms of the rate function. So essentially this is nothing but approximately exponential minus 1 by delta infimum of the rate function of the delta theta process over all norm delta theta greater than epsilon, where delta is a parameter is a small parameter in the noise in delta pt and delta st. So you are looking at a family of densities. Delta appears in delta st in these measurement errors, also in delta pt, and you get the rate function of delta pt and delta st after taking this parameter into account. For example, if delta pt is a Gaussian process, you will put a root delta into delta pt, you will put a root delta into delta st, and you will compute the large deviation rate function for these processes. It will be something, okay, you know how to compute using Schilder's theorem or using the formula for the rate function of a Gaussian process, and you can get the rate function for delta theta t by using a transformation of the rate function formula, and you can minimize this quantity. Anyway, what happens if the whole thing is a field? Suppose you want to estimate not a probability density function, but a probability density functional of the field. For example, suppose you take a Dirac wave function. Suppose psi x is the Dirac wave function of a particle, and you consider its Lagrangian. Consider this Lagrangian when it interacts with an electromagnetic field. So you put psi x bar into gamma mu I dou mu plus E a mu minus m times psi x. It interacts with an electromagnetic field. Apart from this, you have the Lagrangian of the electromagnetic field itself. So you can put minus 1 by 4 f mu nu. You can put this. So you get the whole. This is the Lagrangian for the Dirac field of electrons and positrons interacting with an electromagnetic field. Now I want to control the electromagnetic field in such a way such that you get a given transition probability for the Dirac wave function from one state to the other. So if I call this as, let us call this as L of psi without A, okay. So I can write this as L0 of psi plus L0 of A plus Li of A and psi. So L0 of psi is the Lagrangian of the Dirac particle, L0 of A is the Lagrangian of the electromagnetic field, Li A of psi is the interaction Lagrangian. This last interaction Lagrangian can be read out from here. So you can write L0 psi as psi bar gamma mu I dou mu minus m psi. L0 of A can be written as minus 1 by 4 f mu nu, and Li of A psi can be written as psi bar gamma mu psi into E a mu, that is j mu a mu. So I want to control. Now what will happen is you cannot control the quantum electromagnetic field of the radiation because that is ambient. What you can do is you can introduce a classical control potential del A. So let us say I have the total electromagnetic field is a sum of a classical control potential which I call A classical plus delta A mu, but this is a quantum field. This is a quantum field, this is a classical field, and you see the interaction between the two. So you have if you integrate the actions over all space and over time varying over 0 to t, that means x0 varies over 0 to t and x1, x2, x3 they vary over space. You compute, then you get the action function up to time t of the field st of whatever function, whatever field you have here up to time t. So here you get an action function of the electromagnetic field, or the action function of the Dirac field, free Dirac field up to time t, plus the action function of the free electromagnetic field up to time t, right, that is f mu nu a, f mu nu a, f mu nu, f mu nu, and then you have a interaction action which is given by the interaction between a and psi, you have an interaction between delta a and psi, and you also have an interaction action between a and psi, the control electromagnetic field and psi, a classical and psi, because a is nothing but AC plus delta A. Now this is a quadratic form in psi, a bilinear form in psi and its conjugate, this is a quadratic form in delta A, this is a bilinear form, this is trilinear, it is bilinear in psi and psi bar and linear in delta A, this is bilinear in psi and psi bar and this is linear in A. So you have this, the total action function up to time t can be written as a sum of all these actions, and then you want to control, the aim is to control the classical electromagnetic field with the quantum electromagnetic field varying over all possible configurations, because you are not interested in the quantum electromagnetic field making any transition, it goes from vacuum to vacuum, right. Let us say there are no particles in the electromagnetic field, but you want the fermionic field psi to make a transition from a given state to another given state. Let us say at time 0, so you want psi t 0, psi 0 x to be a function phi 0 and psi at time t to be phi 1. So if you compute the using the path integral, if you compute this transition probability, what do you get? Transition probability amplitude, let us say you call it as AT, the final state is phi 1 for the fermions, the inertial state is phi 0 for the fermions given all the thetas s less than or equal to t, and these theta s, what are these theta s? Theta s are the control electromagnetic field terms, right. So it can be written, the control electromagnetic field is A of s less than or equal to t. So this is nothing but equal to exponential I s0, means up to time t you are taking s0 of psi plus I s0 of delta A plus I, the interaction between psi and delta A, plus I times the interaction between psi and the control field. You are assuming that the control electromagnetic field does not interact with delta I, actually of course it will involve, because when you compute f mu nu you have to compute this as the sum of f mu nu due to the control classical field plus f mu nu due to the quantum field, and then you take the square of this, it will contain cross terms between classical and quantum, but you are assuming that your control electromagnetic field AC, it affects only the Dirac field. So you have to compute this and you have to take a d psi and d delta A over all field configurations, and you have to do it in such a way that psi at 0 is phi 0 and psi at t is phi 1, with delta A varying over all possible configurations of the quantum electromagnetic field. So how do you compute this quantity, and you want to minimize, you want to make, so this will give you the desired transition probability, right. It is a transition from phi 0 to phi 1, you can choose this control field in such a way such that this transition probability from the state phi 0 to phi 1, it tracks a given a desired transition probability from phi 0 to phi 1, or you can take the final state as arbitrary, as an arbitrary set coming from as any element in a set in a finite set of desired final states, and compute these transition probabilities for each phi 1 in the set of final states, and you compare it with, you match it with the desired transition probabilities from phi 0 to the corresponding phi case, and you calculate the control electromagnetic field. Now this can be computed in terms of the propagator. You see, suppose you look at, let us just look at what this looks like, this expression. First you integrate with respect to delta A, first you integrate with respect to delta A. So you have e power I is 0 of delta A, you take this, and then you have plus I Si with psi and delta A, that is all, delta A comes there, no other way it can come, and you put d delta A. This is done over without any constraints, this is evaluated. Now this can be evaluated as approximately e power I S0 delta A then you can write it as 1 plus I Si psi delta A minus 1 by 2 factorial Si psi delta A square. Let us say you go up to order 2 terms delta A, so this is an approximation. Now since S0 delta A is a quadratic form in delta A and Si of psi delta A is linear in delta A and quadratic in and bilinear in psi, this term won't contribute. So the first non-vanishing term which contributes is e power I S0 delta A into this. But what is Si of psi delta A? Si of psi delta A is nothing but integral psi bar gamma mu psi x into delta A mu, right, d4x. So if you square it, what do you get? If you square it, you will get psi bar x gamma mu psi x multiplied by psi bar y gamma nu psi y into delta A mu x delta A nu y d4x d4y. And if you take the path integral with respect to the unperturbed Lagrange action of the electromagnetic quantum electromagnetic field, you will get the propagator of delta A mu. So you will, because A mu delta A mu is, you are taking a vacuum expectation value, you are interested only in the fermionic transition from phi 0 to phi 1 with the electromagnetic field remaining in the vacuum state. So you will get T of this quantity, it will be the propagator, and you will get other terms in this. So what will happen is that if you compute this quantity e power I S0 delta A times this thing, what do you get? You will get e power I S0 delta A times minus half integral, here you will get Si delta A psi square and you are taking d delta A, right. So what will this approximately be? This will be equal to minus half the propagator of delta A. So you can write this as psi bar x gamma mu psi x then psi bar y gamma nu psi y into the propagator, that is T time ordered vacuum expected value of time ordered products of delta A mu with delta A nu y d4x. So d4x d4y, if you integrate this over this, right. So this propagator will come into the picture and you let us, and this can be this is a 4th degree polynomial, this is a 4th degree in the Dirac wave function. So I will call this function as say some f of it will be dependent on f of psi alone, okay, it will be dependent on f of psi alone. So what is the total path integral, total amplitude of scattering in time t from phi 0 to phi 1, okay, given the control field AT, as less than or equal to t is approximately equal to integral e power I, the action for the Dirac field plus the action of the Dirac field interacting with the control electromagnetic field into Fb of psi, then you put d psi bar with psi at 0 being phi 0 and psi at t comma this being phi 1, and then you take the magnitude square of this quantity, you take the magnitude square of this quantity, take the magnitude square of this quantity also, and you match this to, you try to match this to a given transition probability phi 1 phi 0 by adjusting the values of A, this control electromagnetic field AC, by differentiating with respect to AC here and so on. So you can see that S0 psi, what is S0 psi? S0 psi is simply equal to integral psi bar x gamma mu dou mu minus m psi x d4x, and this is S0 S, this is the interaction action. Si of A psi, f of psi AC, this interaction between the control electromagnetic field and the Dirac wave function, this is nothing but psi bar x gamma mu psi x multiplied by AC mu x d4x. So it is a linear combination and you can design the neural network in the correct way. That means that when you have, let us say you have a desired set of final states phi 1 k, k equals 1 2 etc. m, it is a set of final states, and you want this to match to p t phi 1 k phi 0 for each of this. So, you are computing a t using this method. So, it is nothing but phi 1 k phi 0 given a s, s less than or equal to t, you take mod square and take minus p t phi 1 k comma phi 0, and you take square of this, you take the square of this and you sum over all the k's, k goes from 1 to m. That gives you the total discrepancy between the desired probability, transition probability from phi 0 to one of the elements in the final set phi 1 k with what is computed using the path integral, and you try to minimize this with respect to a by using the variational stochastic gradient formula. That means a at, you call it as AC. So, AC at t plus delta t comma this comma x is equal to AC at t plus delta t, sorry, AC at t comma x minus mu of delta by delta AC of Tx of this quantity. This whole quantity you put here and you calculate the variational derivative. Of course, you can also ask some more interesting questions, like what happens if there is a small random perturbation in the control potential, in the control electromagnetic field, or there is a small random perturbation in the current field coming from the Dirac current interacting with the electromagnetic field. In that case, you have to take a further stochastic average over all these random quantities. For example, if you have, if your a mu consists of a classical electromagnetic field plus a classical random electromagnetic field plus a quantum electromagnetic field, where the statistics of this is known. Likewise, your Dirac current is psi bar x gamma mu psi x, but you have a small, you put an additional control current here, classical control current here, and apart from that you have a small random classical random current field interacting with the bosonic field delta with a mu. So, in that case you are going to look at, so in that case what are the terms that will comprise the total action? The total action will be, it will involve the action for the free electromagnetic field, for the free Dirac field, plus the action for the free electromagnetic field, quantum electromagnetic field delta A, and the interaction terms will be many. There will be an interaction between the Dirac field, quantum Dirac field, and the random electromagnetic field. There will be an interaction between the Dirac field and the, let us remove the index mu, okay. There will be an interaction between the Dirac field and the quantum electromagnetic field as we just saw, and there will also be an interaction term between, say, JC, the classical current field and the quantum electromagnetic field delta A, and there will be an interaction term between the classical current field and A, I think those you can ignore. So, there will be an interaction between the classical random fluctuations in the current and the electromagnetic field. So, when you take all these things into account and compute the path integral, then you have to integrate over both the field psi, the quantum Dirac field psi over the quantum electromagnetic field delta A, and when you compute the transition probability you have to take the magnitude square, and then you have to take the average of this magnitude square with respect to the probability distribution of these random perturbations, like delta in delta A mu is a random field and delta J is a random field. So, if you take that, so essentially you are going to compute the transition probability in which, let us say, the initial state is one in which the Dirac field is in the state phi 0, let us call it as phi 0 Dirac or phi 0 psi, and the photonic field is in the state phi 0 A, and from here it goes to the state phi 1 psi phi 1 A, makes a transition. So, you will get a transition as phi 1 psi, phi 1 a, okay, from here to here, phi 0 psi, phi 0 a, and this is the function of the, it will be a function of the control electromagnetic field, it will be a function of the control current field, which are both classical here. It will also be a function of the random perturbations in the electromagnetic in the classical electromagnetic field, which is controlling and a random perturbation in the current field, which is controlling. When you make the path integral, when you perform the path integral between these two states, and you take the magnitude square and take its expected value, the expected value is taken with respect to delta A and delta J. So, you are taking it with respect to delta A and delta J, and then you minimize this quantity, you try to match this quantity with a desired transition probability, namely phi 1 psi, phi 1 a, from phi 0 psi to phi 0 a. You try to match this by minimizing the distance between this, the difference square, and you can do it for several final states by replacing phi 1 psi phi 1 a by phi 1 k psi phi 1 k a here, and summing over all the possible final states, and then designing the neural network. That is all I wish to say here. Thank you.